Every time you drive across a suspension bridge, you are trusting your life to thousands of tons of steel tension you cannot see and likely do not understand. You simply assume the cables will hold. When you board a plane, you don't calculate the aerodynamic stresses on the fuselage or the fatigue life of the rivets in the wings. You expect the aircraft to safely cross the sky. This structural integrity results from a rigorous, hidden discipline, modeling how a joint absorbs physical pressure and identifying exactly when it might give way. Human intuition is often biased by what happened recently, but at this scale, guesswork is dangerous. We need to quantify the probability of survival using more than just an educated guess. These structures remain standing because an engineer mapped the likely failure modes on paper, reducing the risk of a real-world catastrophe to a calculated minimum. The natural state of any production line, supply chain, or physical system is chaos. Materials wear out, temperatures fluctuate, and measurements constantly drift. Reliability engineering provides the framework to isolate these uncertainties. We can measure the variance, model it, and then design the system to handle it. Moving from an observation of a world that seems to work to a mathematical proof of its survival is the defining shift of the discipline. Consider a coastal town that relies on a seawall for survival. The ocean's threat is highly variable. Storms do not arrive with uniform intensity, and planning for the average surge would leave the town vulnerable to any severe weather. This histogram shows historical storm surge heights. Engineers use the mean and standard error to calculate structural requirements from past surges. As you collect more data, your estimate becomes more precise, and the standard error shrinks. This allows for meaningful comparisons across different regions. Mastery of these descriptive statistics is what allows an engineer to define an unpredictable coastal threat as a calculable risk. In medical manufacturing, failure isn't just a loss of efficiency, it can be a loss of life. Critical components must be guaranteed to function throughout their required lifespan. This physical acceleration model plots a part's lifespan against the inverse of temperature, simulating years of wear in the lab. Tracking failure rates under high-stress conditions lets us extrapolate along this dotted line, predicting lifespan under normal hospital use. Breaking a product in the laboratory is what provides the data necessary to ensure it will survive its mission in the field. Transporting vaccines requires a precise cold chain, where even a brief temperature excursion can render the shipment useless. An X-bar control chart tracks environment averages over time. While the process is stable, data points stay within the dashed control limits. If a point crosses the upper limit, it signals an assignable cause, a specific shift that must be addressed before the vaccine fails. Identifying this statistical drift in real time is the exact mechanism that prevents a compromised product from reaching a patient. In complex system architectures, the arrangement of components determines survival. Component C is a series system. One failure halts the chain, but A and B are in parallel. This redundancy allows the system to survive if one component fails. Reliability comes from designing architectures that anticipate and absorb inevitable component failures, using redundancy to ensure the system survives its parts. This course marks your transition from a user who trusts systems to an engineer who calculates their defense. You will model these physical realities using either R or Python, taking raw, variable data and organizing it into mathematical models. Fluency in this code allows you to identify vulnerabilities and address them long before they manifest in the physical world. The ultimate measure of success for a reliability engineer is that the public remains oblivious to their work. When systems function as they should, disasters are avoided, and the people you protected will never have a reason to know your name. Providing this invisible safety is a fundamental responsibility of the systems engineer.